there's two stages of this section. We're going to look at how you use calculus to tell where functions increase and decrease. Then we're going to learn something called concavity. Okay, and these are all talking about behavior of graphs. So there's tons of graphing in this. And then when we're done with this, the 4.3 is a real short section that just sort of puts this all together and teaches you how to do some of the graphing. So to begin with on this then, the first thing we want to look at is just kind of go over these basic definitions as we're learning this then. Okay, so basically we would call a function monotonic if it's either increasing or decreasing. And we've already seen that before. Functions can go through periods of time where they increase, they can decrease, and then they can do different variations of that in all kinds of different ways. So basically the main thing that we want to talk about here is what is the definition of a function when it's increasing and decreasing, and how does this relate to calculus? These two diagrams I put on here will kind of explain this. I mean, it's real easy to understand what increasing and decreasing means on a function, but the definition's kind of technical, so you want to see if you understand the definition on this. So the idea with this is going to be, if you're increasing, so this right here would be an example of a function that's increasing, and we're just looking at this idea. From here to here, we've got some interval, so you're always increasing from left to right on this. So what's happening to the y values from left to right is, what are they doing? They're getting bigger, right? Okay, so the y values are always getting bigger. So what we say is, if you have 2 points, x1 and x2, those are 2 points that are x values on your function. If all of these y values are bigger and are always bigger, so if this value right here, if this y value is bigger than this y value, then it's going to be increasing on that interval, like that, okay? Now remember, x1 and x2 are arbitrary. They can be anything, okay? So the idea is, if x2 is larger than x1, then f of x2 must also be larger than f of x1. So that just means if this x value is bigger than that x value, this y value is bigger than that y value, okay? Now in layman's terms, you already know this. What does increasing mean? It just means y values are getting bigger, right? Okay, or you're going uphill, okay? Like up a roller coaster or something like that. That's not very technical, but what we're trying to do is kind of get the idea of a more technical definition. Now decreasing is just the opposite of this. So this function right here would be decreasing right here. So what's happening on this, they're just saying, okay, if this x value is bigger than this x value, well then what's happening to the y values? They are smaller, right? So this y value right here, which is represented by f of x1, and this y value, which is represented by f of x2, well, this value is less than that value, right? Okay, so that's the idea. So the idea would be if you're increasing or decreasing, increasing the y values are getting bigger, decreasing the y values are getting smaller on some interval, okay? Now that's not really the calculus yet, that's just technically what we mean by this. Here's the calculus, and we've already talked enough about this, that if you're increasing, now like this right here is an example where you're increasing, what is happening to these tangent lines? What kind of slopes do you have on these tangent lines? They're positive, aren't they? So what you have is, anytime your tangent lines have positive slopes, then your function is going to be increasing on that interval, right? It has to be, okay? And if you have negative slopes, like you have here, the function is going to be decreasing, okay? So if we're going to figure out, just given a function without graphing it, where it's increasing and decreasing, it's going to have a lot to do with the derivative and seeing where that slope of that tangent line is positive or negative, okay? So basically, this is what we do. This is the general test, and then we'll start kind of looking at some examples. So basically, if you have to be continuous on an interval, okay, and you have to be differentiable on an interval. So if you're looking at every point on an interval, you have a continuous function and it's differentiable everywhere in that interval. If the derivative is positive, okay, as it is here, if that derivative is positive, then you're going to be increasing. If that derivative is negative or less than 0, then you're going to be decreasing. So does that make sense? Okay. What does a derivative give you anyway? It gives you a slope of a tangent line, right? So what's happening here is the slope of the tangent lines in this diagram here are positive, and in this diagram they're negative, so that's how you tell whether you're increasing or decreasing, okay? All right, so let's do a couple of things. So what I want to do on this next page here is I want to look a little bit at just giving some information, seeing if we can draw a graph out of this, okay? So this is kind of a typical kind of exercise that I like to have students to do to see how well they understand the calculus behind this. So the first thing that's going on this is this piece right here. That piece right there says the derivative is negative. It's less than 0 on an interval negative infinity to 2. So if the derivative is negative, what does that tell you about the graph? That's what I just said. Increasing or decreasing? Decreasing, okay? So let's write a little note to ourselves that we know that we are decreasing on that interval negative infinity to 2, okay? The next thing it says is the derivative is greater than 0 on an interval 2 to 5. So what would that tell you if the derivative is positive? It tells you that we are increasing. Okay, and there's an infinite number of ways to write this graph. The idea is just kind of that you can create something that's valid, okay? And then the last thing on here would be the derivative is negative on 5 infinity, so what would that tell you? That you're decreasing. Okay, so what we're going to do is we're just going to try to draw a graph on this. Now this is a limited amount of information, but it's enough on here to figure out, you know, to draw a pretty rough graph on this. So let's just draw like a coordinate system. Okay, and let's kind of label out our x-axis. So the key thing is we need to look at over at 2, and then all the way up to 5, so that's kind of where the graph, what the key values are. It doesn't really matter what f of x is, because I don't even really tell you what f of x is. So that's going to be my x-axis and my f of x. So what we're going to be doing is when we're less than 2, the function's going to be decreasing. So just kind of draw something, however you want to, just make sure that it's always decreasing until you get to 2, okay? Then, from 2 to 5, it looks like the function is going to start increasing again. So we just need to make the function kind of turn around and do something like this. And then once it gets past 5, the function's going to decrease again. So we'll do something kind of like that. Okay, that's just one example of what that function would look like. Now, a couple of things that we've learned and that we're going to be dealing with a little bit more in this section is, what do we call that point right there that I just highlighted?
It's going to 0.
That would be a place where the derivative is 0, but what do we call that point? We call it a local minimum, right? Okay, so we do have a local minimum there, and what happens on a local minimum is it means that the graph changed direction. It went from decreasing to increasing. Now, what do you call this point right here? You call that a local maximum, okay? So we talked a little bit about that in section 4.1. So it's going to turn out in this section, we're going to have a strategy for figuring out maximums and minimums as we do that, okay? So that's one way to draw that, okay? There are many ways to draw that. But that's the idea. Does that make sense? Okay. All right. Let's see what we come up with on the next one here. This one has a few more pieces of information on it now. Okay. So first of all, we have the derivative's undefined. Okay. Now let's think about what that could mean. If a derivative, if something's not differentiable, what would that tell you? What are some possibilities that would tell you?
Sure.
You might have a sharp point, okay? You could. Now remember, we can be creative on this problem, okay? We could have a sharp point or a cusp, right? Okay. If it's not defined, we could also have maybe a break, right? Some sort of a break, right? You'd have maybe an asymptote, like a vertical asymptote or something like that. There's all kinds of possibilities. So you got a place where the function's does not have a derivative, okay? At -1, you don't have a derivative, okay? Then if we move on, Okay, what does this piece of information right here tell you? This says the derivative is greater than 0. What does that tell you? Function's increasing. Okay, so on that interval, negative infinity to negative 1, we're increasing. Okay, then we also have this. This says the derivative is less than 0. So what does that tell you? We're decreasing, right? Okay, so what we're going to do is let's just draw a coordinate system. Let's see if what we come up with. Okay, there are many ways to draw this graph. You just got to come up with something. Okay, so let me try that again. Okay, so let's see. We need to look really at negative 1. Negative 1's kind of the key point on here that everything's based on. So one thing it's saying is on the interval negative infinity to negative 1, the function's increasing. Okay, so just make the function increasing however you want to. Doesn't matter how high you make that thing go. Okay, and then we're going to be decreasing the rest of the way on here. This thing's just not working. Okay, so if I was going to make this decrease the rest of the way, now one thing I could do is I could make a sharp point right there and then just make it go something like that. Okay, that should basically tell you everything we have in here. We're increasing from negative infinity to negative 1. We're decreasing the rest of the way, and we're not differentiable right there. That's one way to do it. There are other ways to do that. Couldn't you have done like an asymptote maybe? And you could have had something maybe kind of like this, an asymptote. You could be increasing, and then you could be decreasing. You could do that if you wanted to. Okay, there's all kinds of ways as long as you are representing that it's not differentiable at x equals negative 1. Okay, does that look any good? Okay, all right, so that's one thing I would want you to be able to do, and that's just kind of an exercise that helps you understand how the calculus works on this. Okay, so we're going to start with some real simple examples on this. So, and I've done a lot of graphs on this. Instead of taking up time to get our calculator and do graphs, I went ahead and just represented some of these graphs. But technically, we're supposed to look at the graph at the very end of the problem for interpretation. So, first of all, what we're going to do on this is we're going to take this function just using calculus methods, and we're going to figure out where it increases and decreases. Now, I already know that's a parabola, right? But again, the point is, let's look at calculus and then let's look at the graph and see if it makes sense to us. So here's what you do. The very first step, and you can write this down if you want to, the very first thing that you do, if I want you to find where a function increases and decreases, is you want to find critical points. We did talk about that. I don't know if you remember what I was talking about on that. You guys remember what critical points are? What are they?
Maximums, minimums.
But not quite, okay? They can be max and min. What are they? They have something to do with the first derivative, okay? It's basically critical points are where the first derivative is 0 or where the first derivative is undefined. Okay, so you got to start these problems by finding a derivative. That's the calculus part of that. So that's step one on this problem is let's find the derivative. Well, this is a real easy derivative. That's f of x equals 2x, okay? So what we're going to do is we're going to set that equal to 0. See, that derivative's always defined because that's a line. It's always defined. So what we do is we set that equal to 0. You can solve that in your head so you get basically a critical point at x equals 0. So you might write on there critical point at x equals 0 like that. Okay, now what you're going to see me doing a lot on these problems today is tons of sign charts. Okay, so what I'm going to do on this now is we're going to make a sign chart. Just kind of draw yourself a number line, and the critical point, the only critical point we have is x equals 0. So if we want to figure out without looking at the graph where it increases and decreases, we just analyze the derivative and that's it. So what I'm going to do is I'm going to take what I call test points. So I'm going to take a point that's less than 0. It's your call too. Let's keep it simple. Let's call that -1. So what you do is you take that test point and you plug it into your derivative and you get a negative result. You don't care that it's -2. What you care about is it's negative. So if the derivative's negative, what does that tell you about increasing and decreasing? tells you we're decreasing. Okay, so we have now got that figured out, see? Okay. Now what you want to do is you want to take a test point, and it doesn't matter what you pick because it'll always work the same way. Let's take 1. 1 is bigger than 0. Plug it into the derivative 2x. That's going to give you a positive. So if the derivative is positive, what does that tell you? Function's increasing like that. Okay? Problem done. So the idea is find your critical point and then do test points. So you're going to do tons of sign charts on these problems, okay? Tons of them. Now, we just formalize this. So the idea is going to be this when we write the answer. We are decreasing when we are less than 0. So how do you write that? You say negative infinity to 0, and then you put a parenthesis on that. These things are always open intervals, by the way. Okay, that's important too. Don't use a closed interval on that. Be sure you use open intervals on that. Okay, because that critical point is, we don't consider that to be increasing or decreasing. Okay, and then, did I write that wrong? I sure did. Okay, it's increasing wherever the derivative is positive. So that should be where to where? 0 infinity, and then decreasing is negative infinity to 0 like that. Okay, open intervals, that's a good thing to write a little note of like that. Okay. So that's the first thing you do. Then basically the second step that you're going to do on these is a sign chart. Okay, and that's going to explain lots of things too. So if you look at the graph, you can tell that, of course, you're decreasing here, like we said, then you're increasing there. Okay, that's it. Okay, does that make sense? And that's a real simple example. The derivatives, of course, are going to get more complicated than that, but we're going to kind of start fairly easy here. Okay, so let's look at this graph. And again, what we're going to do is find critical points, find the intervals where it increases and decreases. Then we'll look at the graph later. Okay, I just wanted to put the graph on there to save a little time. So how do you find critical points again? First derivative, you see where the first derivative is 0 or undefined. Okay, so if we're going to differentiate this, we need to write this, of course, as x to the negative 1. Okay, then when we do this derivative, that's going to be power rule, so that's going to be negative 1x to the negative 2, so that's negative 1 over x squared. Okay, now when you get to doing this, see, what you always do is you always take your derivative and set it to 0. Okay, is there a solution of this equation? No, there isn't. Okay, and if you don't see that, students don't always see that. If you cross multiply, look at the crazy stuff that would happen. You would get x squared equals negative 1, and you would square root both sides, and you would get an imaginary number, right? So this derivative is never equal to 0. It never is, okay? So we would just say, you know, f prime of x is never equal to 0. So we don't have a critical point in that regard. However, is this first derivative ever going to be undefined? Yeah, where at? At 0. You can't have a 0 denominator, right? Okay, so you can't have that. So you basically have a critical point at x equals 0. Okay, that's because it's undefined. So sometimes, and a lot of times students forget this, they're so used to setting the derivative equal to 0 to find a critical point. They can also be places where the derivative is undefined. Okay, all right, does that make sense to everybody? Okay, so what we're going to do now is we're going to do our sign chart. So what do? You draw just a little number line. And you always want to look at your critical point, and you're going to see some examples here in a little bit where we have several critical points. What I like to tell students to do on this is put a U, okay? That way it's undefined. That way you know the derivative doesn't exist there. You're not differentiable there. And then from here, it's nothing more than just a matter of doing test points again. And sometimes you can do all this in your head. So you take your derivative, and we're going to replace that x squared with negative 1. So what do you get? You get negative 1 over 1, so you get a negative. Okay? So that means the function's going to do what? Decrease, right? Okay? All right. Then we take a test point that is bigger than 0, like, say, 1. So what we have is negative 1 over 1 to the second. That's negative 1 over 1. So again, that's negative, so that means it decreases again. And these functions don't alternate from increasing to decreasing. They don't have to. They can do all kinds of combinations like that. Okay? So then what we would say is, if we're going to say where it increases, where does this function increase? It never does. So you just put never. Okay, it never does. Okay, now it does decrease, and the thing on this is you got to use two intervals. A lot of times students want to say the answer is negative infinity to infinity. It's always decreasing. No, it isn't, because what's going on at x equals 0? You're undefined. You actually have a vertical asymptote on this problem. So you'd have to break it up into two intervals. You'd have to say negative infinity to 0, union 0 to infinity. You have to. You got to break it up into two intervals. Okay? Now what I did is I put this on my graphing calculator, and this is just kind of a standard window. So if you look at this function, I think you can see on here, okay, isn't it decreasing from there to there? Okay, the y values are getting smaller, so it's going downhill. Then if you jump past that asymptote, isn't it still decreasing again? Okay, so you're starting high and just going lower and lower and lower like that. So the graphical part of this should be something that you use to help you understand how the mathematics is going. I don't want you to do your homework by immediately going to your calculator and putting the graph in, because then you don't have to know anything about calculus. You see what I mean? Okay, that's a graphing part. That'll open up the mathematics of what we're doing. Okay, and sometimes it's real helpful when the problems get more complicated to see that. Okay, now I forgot to put the domain on here. So the domain, we're just going to say set of x is not equal to 0, or you could say negative infinity 0 union 0 infinity. So that's an example of a vertical asymptote. That's a rational function. It's got a vertical asymptote. Okay, not differentiable. Okay, everything good so far? Okay, it's going to get a little more complicated. So if you're getting bored, just hang in there. Okay, it'll get better, but you got to start somewhere. I'll start with easy stuff first. Okay, I'm going to do one more that's easy, and then we'll kind of get to some more complicated derivatives. Okay, so cubic function. All right, if you find a critical point, what do you do when you find a critical point? Okay, you find the derivative, okay, which in this case is very easy. It's 3x to the second. That derivative's always defined. 3x to the second is a quadratic function. It's always defined. So then the next thing you want to do is just take that derivative, set it equal to 0, and solve the equation. Okay, you can do this in your head if you want to. You don't have to go through all these details. You can do this in your head. That's x squared equals 0. Square root both sides, you get x equals 0. So again, we just get a critical point of x equals 0. Okay? So what we're going to do again is once we get the critical point, we're going to make a sign chart on this again and just kind of analyze this. This time what I'm going to do is break this up into x equals 0. You are differentiable at x equals 0 because when we set the derivative equal to 0, we got a value. Okay? So now it's just test point stuff again. So let's use -1 and plug it into your derivative. Always plug into your derivative, not into your function. Okay, so we're going to do 3 times -1 to the second. Is that positive or negative? Positive. What happens if you square any number other than 0? You get a positive, don't you? So if you take any test point, if you take 3 times something squared, aren't you always going to get a positive? Okay. So sometimes you can do all this in your head. You don't have to do test points. So if you plug in 1, you would have 3 times 1 to the second, you'd have positive. So that means the function's increasing there, increasing there. So this one's always increasing except at that one place where the derivative is equal to 0. Okay? So we would write the interval increasing would be negative infinity to 0. 0's neutral because the derivative is equal to 0. And then we would also say from 0 to infinity, and then we would say this function never decreases. And if you look at the graph that I put on there, does that make sense? The function's always increasing. It's always getting bigger. Okay. Would you consider this point right here to be a minimum or a maximum? No. Okay. Remember what a local minimum or maximum is the function's got to change directions. It's got to go from decreasing to increasing or vice versa. So that is not a minimum, and it's also not a maximum. Okay? So remember, if you find a place where the derivative is 0, that doesn't mean it's going to be a maximum or a minimum. Okay? Okay, so any questions so far? Okay, everything I've done so far is very simple derivatives. So some of these will get a little bit more complicated as we go. All right, I want to go over these, a couple of diagrams here. And we've already talked about this, like critical points are not always extremes. When I'm talking about extremes, I'm talking about local minimums, local maximums, okay, or absolute maximums and absolute minimums. The problem we just did is a good example, okay? When we did the derivative of x to the third, set it to 0, okay? That is a place where the derivative is 0 because the slope of that tangent line is 0, okay? So we got that. Here's another example. If you graphed x to the 1/3, you would have this situation, okay? The derivative is undefined at x equals 0. So what would you say about the slope of the tangent line at x equals 0 since it's vertical? What do you know about that? That's undefined. So we would say the slope at x equals 0 would be undefined, okay? That would be a place where the derivative is undefined, but it doesn't mean it's a max or min. That's the thing I'm trying to kind of drive home here. Is places where the derivative is 0 does not necessarily mean it's a max or min. Does that make sense? Okay, the only way to figure that out is to do that sign chart and kind of analyze that. So this diagram right here just sort of shows you lots of possibilities. So you would see the functions increasing here, which means the derivative is 0 like we talked about. Why is the derivative undefined at this point? Sharp point, okay, we don't have a defined tangent line at a sharp point. We often call that a cusp, okay? Then we'd be decreasing. That's because the derivative is negative, so you'd have a negative derivative there. This would be a place where the derivative is 0, okay? And then this right here would be a minimum. That would be a local minimum. Okay, then the derivatives from -4 to 6 are going to be increasing again, okay, because the derivative is positive. Then you're going to have another place where the derivative is 0, and then the derivative is going to be positive again, okay? Is this point right here a max or min? No, so that's not, we would say that's not a extrema. We call max and minimums extreme points or extrema most of the time, okay? So if you look at a graph like this, you want to be able to tell, okay, why the derivative is positive, why it's negative, 0, and so forth. Does that make sense? Okay. All right. Now I think on the next page what I'm going to do is run through some different types of functions. Now I'm going to do several types of functions. This is a little harder, but this one's still not too bad. Okay, if you're dealing with polynomials, then these will probably go pretty smooth for you, assuming you can factor that as. You have to be able to factor that. Okay, so step 1, what do I want to do? I want to find the critical points. How do I find critical points again? First derivative, find out where the first derivative is 0 or undefined. So this one's pretty simple. So let's go ahead and do the derivative. We can do this one in our head. So this is 4x to the third minus 12x squared plus 8x. Okay, so we have that. So what we're going to do, now that derivative is always defined. The reason I know that is because it's polynomial. X can be anything. So we're going to go ahead next here, and we're going to set this. I'm going to just do this to the side. You should have enough room to do this somewhere on your paper. 4x to the third minus 12x squared plus 8x equals 0. So if you're going to find the critical points, you've got to dig to your algebra background and you've got to be able to solve that okay. Now the thing that I would suggest that you learn how to do is notice you have 4, 12, and 8. What's the biggest factor between 4, 12, and 8? So divide everything by 4. Okay, you can also take 4 out as a common factor, but it's just as well to go ahead and divide by it. If you have a constant, you can divide by it. Okay, it doesn't change anything. It doesn't change the solution to the equation in any way. So that's just going to give x to the third minus 3x to the second plus 2x equals 0. Okay, or you can take 4 out, but you're going to end up dividing by it anyway, so you might as well just do that now. Okay, does this expression have a common factor that can come out now?
X.
Yeah, take x out. So if you take x out, you're going to be left with x squared minus 3x plus 2 equals 0. Okay? How about this trinomial, x squared minus 3x plus 2? Do you think that factors? Probably does, so let's factor again. These problems are all about factoring skill mostly. Okay, so I'm going to factor this. This factors as x minus 2, x minus 1. And every time you factor something, I say this all the time, check it. Don't waste your time. If you factor something wrong, you're wasting your time. Okay, make sure it's right. Foil it out, make sure it's right. Okay, so what are the critical points then? Okay, what do? You set that to 0, you set the second factor to 0, and you set the third factor to 0. Okay, now you can do each of those in your head. So your critical points are going to be at x equals 0, x equals 2, and x equals 1. So we got 3 critical points in this problem, so let's just write in our answer blank 0, 1, and 2, like that. Okay? So basically the calculus was just doing the derivative, one step. The rest of that's algebra. Does that look okay to everybody from your background? Okay, this is the section where I find out a lot of times if students can factor or not. You'll find out the same. Okay, you're going to factor some. All right, now what we're going to do is we're going to make a sign chart to kind of analyze this stuff now. Okay, so I'm going to go ahead. Whoops, that's not what I meant to do. So draw a line and let's make a sign chart here. Okay, so put your critical points in order. That's important. Okay, so we're going to have like x equals 0. We've got x equals 1. Then we have x equals 2. Like this. Now, one of the things I want to kind of show you too is once we get this done, I'll show you that the graph is really going to tell you where things are positive and negative anyway. Okay, so what we're going to do is we're going to use test points. So let's see, below 0, let's use -1. It doesn't matter what you choose, you'll always get the same answer. And my suggestion would be that you plug that test point into the factored form. It's a little easier that way. Although technically you could plug it into the original if you want to do it that way. To me, it's just as easy to plug it into the factored form. So let's just go. The factored form is x times x minus 2 times x minus 1. You can even learn how to do this in your head with a little practice. So I'm going to just write the step. I'm going to replace all these x's with my test point, like that. Okay? Now, you don't have to crunch out all the details. Okay? That's a negative. What is the result of what's in the parentheses? -1 minus 2 is a negative number, right? That's all you care about. And then -1 minus 1 is negative, right? So what's a negative times a negative times a negative?
Negative.
It's a negative. So what does that tell you about the function? Increasing or decreasing? Decreasing. Okay, like that. All right, so we know we're decreasing on that interval. Okay, now take a test point between 0 and 1. Let's take like a half or 0.5. You can use a decimal if you want to, but don't worry, you don't have to crunch out any arithmetic. So we're going to plug in again into this factored form. So we're going to replace x with a half. Then we're going to do a half minus 2. And then we're going to do a half minus 1. Okay? And just do this in your head. So a half is positive. What is a half minus 2? Positive or negative?
Negative.
It's negative. Hey, that's all you care about. What's a half minus 1?
Negative.
Negative. What's a positive times a negative times a negative?
Positive.
It's positive. Okay? So that's going to tell you that this function is now going to increase in that interval from 0 to 1. So you're going to have that. Then you just keep going on, doing the same thing. Now I think I was supposed to put in, this I'm going to put in like 1.5. Okay, like there. Okay, again, plug into your factors. So you got x becomes 1.5 times, and then you got 1.5 minus 2 times 1.5 minus 1. Okay, so 1.5 is positive. Okay, what is 1.5 minus 2? Negative or positive?
Negative.
Negative. That's what you care about. Okay, And then what is 1.5 minus 1? Positive or negative? Positive. So it looks like you have positive times positive is a negative. So that means the function is going to decrease like that and so forth. Okay. Then take a test point bigger than 2. It's up to you. I'm going to take 3. So I'm going to plug into my factors. So that's really 3 times 3 minus 2 times 3 minus 1. So that's a positive times positive times positive. That's a positive result, which means the function is going to increase like that. Okay? So that's the result like that. Does that make sense to everybody what I'm doing? Okay? Now, one of the things I want you to look at is here's the graph. Before we write the answer, I want you to look at the graph. Okay? If when you're below 0, it said the function is decreasing. Wouldn't this have negative derivatives right there? Okay? Then between 0 and 1, it said the function was increasing. Wouldn't that be positive derivatives in there? And then negative derivatives? And then positive again? Okay, you guys see what I mean? Okay, so what's happening is the derivatives are changing signs over and over again. So what we're going to say on increasing then is increasing is basically going to be in this region and in this region. Okay, so we just name that in an interval. We say 0 to 1. Union, 2 to infinity, always use parentheses. These are open intervals. And then decreasing is going to be there and there. Okay, so what we're going to say on that is we're going to say negative infinity to 0, union, and then 1 to 2. Be sure that you are careful about your test points. A common mistake that I make sometimes, and students make sometimes, is use their test points as intervals. That's the reason I box them in and kind of make them loud so I don't confuse it with these things. The critical points is where you're naming your intervals, okay? Then put it in your calculator and then see if it's making sense to you, okay? All right, does that look any good? Okay, that's not too bad. That's a pretty basic derivative. And, you know, the derivatives aren't going to be like super hairy on these. I mean, they'll get a little better than this one. We're going to look at enough functions to kind of get a variety. I think for students, usually students do very well if they're polynomials. As long as their factoring skills are up to par, that's not a big problem. All right, now we're going to look at this function, x squared ln x squared plus 1, and we're going to run through everything exactly the same way. So what I'm going to do on this one is we're going to start by doing a derivative to find our critical points. So let's go ahead and start with this. This is probably where some of you guys need a little work, is on doing some of these derivatives with logarithms and other things, okay? So let's go ahead and do the derivative. And you're going to have to, on this one, you're going to have to go through and you're going to need to use a product rule right there. And of course, the derivative of 1 is going to be 0. So really, we got to just pull out the product rule on this, okay? So when we do the product rule, we're going to take the first times the derivative of the second, and you can go ahead and do the derivative of ln x now if you want to, plus this, and that's ln x squared, plus the second, ln x squared, times the derivative of the first, and then of course the derivative of 1 is 0. You don't have to put the 0 there. I'm just doing that for emphasis mainly, okay? So now this is going to be x squared. What's the derivative of ln of x squared?
1 over x squared.
Okay, now be careful. It's 1 over x squared, but then there's a chain rule involved. So you have to do the derivative of x squared, so it's 2x. That's what I could tell on the test, is the chain rule is some of you got it down, some of you do not. And you must get the chain rule down. Okay, that's whenever you have a function other than just x. Okay, now we go ln of x squared, and of course the derivative of x squared is going to be 2x. So now we're going to simplify this. Simplifying is very important on these problems. What do you see happening? Hopefully you see those cross out, so that's kind of nice. So we're going to be left with 2x, and I'm going to write this as ln x squared times 2x like that. Okay, so that is what our first derivative is then. Okay, does that look okay? Okay, now we got to find critical points on this. Now you got to be kind of careful about a couple of things on this problem. When you find the critical points, the first thing you need to do is you need to take that derivative and you need to set it to 0. to see where the critical points are. This thing is always going to be defined. Now, there's a couple of background issues that a lot of times students struggle with. Okay, this is important. If you have an ln, what kind of number can you take a logarithm of? Only positives. That's important. So whatever that argument is must be bigger than 0. And it can't be equal to 0 either. The logarithm of 0 is undefined. But notice on this you have x squared. Okay, so if you do x squared, okay, you should be okay because it's a positive number. However, if x was equal to 0, then wouldn't you have the ln of 0 squared? Okay. Now, if you do the ln of 0, now what does the ln of 0 really mean? It really means the log base e of 0. So it really means e to what power is equal to 0. Can you take any number and raise it to a power and get 0? You cannot. Okay, so remember, an ln must be you can only take an ln of a positive number. So one of your critical points is going to be 0. Okay, you're going to be undefined at x equals 0. Okay, the graphing calculator that I did is not going to show that, but there's technically a bubble in that problem, and I'll show that. Okay, so let's go ahead maybe now and put a bubble right there. Okay, there's a bubble there. You're not, the derivative doesn't exist there because you have a discontinuity. Okay, now what we're going to do is we're going to go ahead and take the derivative, which is 2x. You want to take 2x plus ln x squared times 2x and set that equal to 0. Okay, how in the world do you solve an equation like that? You factor. Factoring is all over the place on these problems. Does this expression right here have a common factor in it somewhere? 2x, take it out, good. Okay, so we got 2x. You have to multiply 2x by 1 to get 2x. You have to multiply 2x by ln x squared to get that right there. Okay, just check it in your head. 2x times 1 is 2x. 2x times ln x squared is that expression right there. Then what you got to do is, since you have two factors, you got to take each factor and set it equal to 0, and you got to solve each equation. Okay, usually it's the ones with the logarithms that students struggle with because of background issues. Okay, so what we have on this one is we already got this critical point, x equals 0. So we've already got that kind of taken care of right there. We already figured that out. Now we need to solve this equation. 1 plus ln x squared is equal to 0. So the way I'm going to do this is I'm going to do ln of x to the second, okay, is equal to -1 after I do that. Okay, and then the way you got to solve equations like this is you got to do this. Now watch this carefully because this is where students struggle a lot on these problems, is logarithms and background issues from college algebra. An ln is a log base e. How do you solve an equation like log base e of x squared equals -1? What do you have to do?
Bring the x or the s.
Right, yeah, the exponential form, right? I think that's what you're thinking. Maybe. That's what I'm hoping anyway. So you say e to the -1 is equal to x squared, right? Okay, you guys remember that? Okay, if you don't, you need to work on it and review it, okay? All right, so this is going to be e to the -1 equals x squared. Now, e to the -1, you could actually write that, and I'm going to just kind of squeeze this over here a little bit. You could write that as 1 over e equals x squared, right? You can make that negative exponent positive. Now, what are you used to doing when you have x squared equals a number to both sides? Square root, not forgetting, of course, the plus or minus. So those are going to be two more critical points right there, and your critical points aren't always whole numbers. They can be mathematical expressions of all sorts. So we have x equals, now the square root of 1 is 1, so I'm just going to say plus or minus 1 over square root of e. Okay, and we can leave it there. We can rationalize the denominator too if we want to. So we would have two other critical points would be x equals plus or minus 1 over square root of e. So we actually have three critical points on this problem. Okay, now tell me how that algebra looks to you. Anything you need me to go over on that?
What happens if you
The -1.
Okay, right here. What did I do with e to the -1? How do you make a negative exponent positive? You bring it down to the bottom. So I wrote that as 1 over e to the first. And that's important, right? Like x to the -2 is 1 over x to the second. So you've got that, okay? All right, so we've got our critical points now. Now, one of the things you're going to have to do on this a little bit is when you make your sign chart on this, which is what we're going to do next, we're going to draw like a number line on here. And we're going to put our critical points. So we have x equals 0. And one of the things we said on that is we said the derivative didn't exist there. Okay, and the reason is because if you look at your derivative, I'm going to highlight the derivative right here, is remember the ln must be, that expression you're taking the ln of has to be greater than 0. And if x is equal to 0, you have a major problem. You can't take ln of 0, right? Okay, so we got our test points now. Now what we're going to do here is we're going to do, and we're going to use a decimal on this. We can use our calculator and get a decimal. So this is going to be 1 over square root of e here. And then over here, we're going to have negative 1 over square root of e like that. Okay, so that's going to take care of that. Okay, now what I'm going to do is I'm just going to take my calculator, and you can do the same thing if you want to. I'm just going 1 divided by square root of e. Okay, and I'm going to pull up my calculator so I can kind of show you where all the keystrokes are and everything on this, in case you don't know. So just in a standard window, I'm going to go 1 divided by square root of e. Now your e by itself is right above your division symbol. So you'll see your pi and then your e. So you can go second division symbol and do that. And let's just get a decimal, like 0.6 is good enough. We'll say 0.6, okay, as we're doing that. So you're doing that, and I'm just going to write a little note to myself that this is really about 0.6. And this is really about negative 0.6 like that. Okay, all right. Now what we got to do is we got to plug in test points into this derivative. The derivative I've got highlighted kind of in this blue color right there. That's what we need to do. Or it's, if you want to, and a lot of times it's even better to plug into this factored form. Let's actually plug into that factored form of the derivative. Okay, it's a little bit easier to work with factored form. So I'm going to write this here. Our derivative f prime of x is 2x times 1 plus ln of x squared. When you're doing sign charts, you want to try to do things a lot in your head because it'll save you a lot of time. Okay, so let's take a test point out here that's below negative 0.6. Okay, and let's make it, how about -1? Okay, let's use that. Okay, if you plug it into this derivative, what you're going to have is you're going to have 2 times -1 times 1 plus ln of x squared. Now, I'm not even bothering to put the x squared in there because isn't that going to be positive anyway? Okay, so what you're going to get is 2 times -1 is going to be negative. This whole expression right there is going to be positive. Okay, if you take an ln, and you can use your calculator if you want to, if you take an ln of a positive number, you get a positive number. Okay, if you do that. So you're going to end up having 1 plus the ln of some positive number like that. So that's going to be negative. So that's going to tell you the function is going to decrease right there. So it's all kind of the same. Now take a number between 0 and negative 0.6. We could take something like maybe negative 0.1 and plug that in and see what happens. Okay. So if you do this, you would have 2 times negative 0.1 times, and then you would have 1 plus ln of negative 0.1 squared. Okay. Now one thing on this one, and you got to kind of use your calculator a little bit on some of these problems. So I'm going to put this in the calculator like this. If I do 1 plus ln, and if I put this like this of negative 0.1 to the second, okay, whoops. Oh, I didn't put that in right. You got to go like this. You got to go ln, and then you got to, I think, do this expression like this, or it won't do it right. I think you got to go negative 0.1 to the second, like this. Okay, that gives a negative number like that. Okay, so what we're getting then is, if you look at this now, 2 times negative 1 is negative. Okay, and then this thing that I just did on the calculator gave me a positive. So I have a negative times a positive is a negative, okay, like that. Or did I get a negative? I got a negative on the calculator. Yeah, sorry. I got a negative times a negative. It will if you look at the graph that I got on here. So it's basically a negative times a negative, so it's a positive. So that means the function's going to increase like that. So let me pull up the calculator and show you what I did. What I did is and you can do this in 2 steps. If you did like negative 0.1 times itself, well, you get that positive number. So you're really doing the ln of 0.01. Okay, now what 0.01 is 0.01 really is this. If you think about doing the ln of positive 0.01, that's really the ln of, and that is really, what is that, 10 to the negative 2. 10 to the negative 2 is 0.01, and remember you can do this. You can go negative 2 times ln of 10, it's just negative 2 times a positive number, so it's negative. Now you want to use your calculator to kind of assist you with that a little bit. And then by the same logic, now I'm not going to go through all the details of all of these sign charts, but what you would end up having, if you did a test point here of 0.1, you would get the same thing. You would have 2 times 0.1 times, in parentheses, 1 plus ln of 0.1 squared. If you worked that out, you would get positives again, or negatives this time, I think is what you'd get, because you would have that negative logarithm again. So you would have like positive 2 times a negative would be negatives. So that would mean that you're decreasing, like that. And then when you go out here, if you took like a number like 1 as your test point, and you did 2 times 1 times 1 plus ln of 1 squared, you would end up on this one getting a positive times a positive. And I'm not going to go through all the stuff on the calculator, because problems like this you can use your calculator to figure that out. So then you've got how your function's going. Okay? Now, the idea of when you get into stuff like this where you have kind of funny critical points like this, you could use your calculator to assist you with that a little bit if you wanted to, and then you could go through and figure out your sign chart that way. Okay? All right, is there any question on that? That's a harder problem, no doubt. Yeah. You okay? Okay, the sign chart, just if you need to go to your calculator to help you a little bit, I'm okay with that. Now, one thing I want to show you on this now is notice that you have negative derivatives. Look at your graph, positive derivatives, negative derivatives, and positive again. So the sign chart, the graph tells you the sign chart, doesn't it? So there's a tendency sometimes on students to say, well, why can't I just get my graph out? Well, you can do that. If you look at the graph, you're not doing any calculus, okay? This is a calculus class. I'm teaching you calculus, right? You can use that to assist you a little bit with your sign charts. I don't mind that on the more complex problems. You know, get a graph out and we'll use that to help you with that sign chart. So what we're going to do now when we get the answer to the problem, we're going to say we're going to increase, it looks like, on these 2 places. So we just write the intervals. So we say, and we have to use the exact answer, so we're going to say negative 1 over square root of e, comma 0, union, and then 1 over square root of e, comma infinity. Okay, so you'll have kind of intervals like that you have to do. And then decreasing is going to be in these 2 areas that I'm highlighting. So on that, we're going to say negative infinity to negative 1 over square root of e, and then union, then you would say 0 to 1 over square root of e, like that. Okay? Now, one thing I do want to pull up my calculator, I do want to show you guys something on this too. If you got your calculator, do this with me. I think I'd like you to do this problem with me on the calculator so I can just show you a couple of things that are kind of helpful for homework and stuff. So I'm going to go through and put in, go to y1, and I'm going to put in x squared, ln of x squared. Now you have to put this in like this, basically. You're doing ln of the whole thing x squared, and then you're doing plus 1. Now I'm going to do this just in, I'll give you a window that's similar to what I have on my handout. So I'm going to go like, say, -5 to 5 by a scale of 1. And let's just go like, say, something like -2. I think that's how I did this. I may have to adjust this window. So -2 to 6 or something like that. Okay, just kind of use the window, roughly what I've got on my picture there. And I wanted to show you a couple of things on this. One thing that you can do graphically, if you're kind of worried about that critical point of 1 over square root of e, you can do this on your calculator and try this. So if you just go trace, one of our critical points was 1 over square root of e. So if you type trace, then you go 1 divided by square root of e, using your e symbol right there, it should blink on that minimum, see? Okay, so that pretty well visually verifies that, doesn't it? Okay, you could also trace at 0. Another critical point was 0. So why in the world does it just leave it saying y equals blank? Because you weren't differentiable there, okay? So that's the idea. I said there's a bubble there, so your graphing calculator is not kind enough to show you the bubble that really exists there then, okay? So you can use your calculator to check just about anything you want to on these, okay? All right, let's move on and I want to kind of